Hello class, in previous lessons you've learned how to use the given information about a right triangle to find the remaining angles and sides of the triangle, and that's great. However, not all triangles are right triangles. So what do we do when the information that is given is about an obtuse triangle or an acute triangle? Well, there are two laws that can help, and in this video I'll be introducing and proving the law of sines. In later lessons, you will learn about the law of cosines. Let's begin. So given triangle capital A, capital B, and capital C with sides lowercase a, lowercase b, and lowercase c, the following ratios are all equal. And I'm going to box them. These ratios are known as the law of sines. And I would like to emphasize that capital letters represent angles and lowercase letters represent sides. So what information about any triangle is needed to be able to apply the law of sines? Well, from geometry, there are 5 ways to determine if two triangles are congruent or similar. Of the 5, 3 of them provide enough information about the triangle to apply the law of sines. And they are angle, side, angle, side, angle, and side, side, angle. Starting with angle, side, angle. If the problem provides 2 consecutive angles and their included side, that is enough information to find the value of the 2 remaining side lengths and the remaining angle. And what's nice is that the information that's provided is only one triangle. You can't find 2 triangles or 3 triangles, just one triangle is possible with the information that is given. Next is side, angle. So given 2 consecutive angles and any side that's not included, you can apply the law of sines. And what's nice is that after applying the law of sines to find the 2 side lengths and that other angle, only one triangle is possible. Finally, we have side, side, angle, and we're going to call that the ambiguous case. Because if the problem provides a side, and then an angle, it is possible that the problem provides information and no triangle exists for that information. It's also possible that only one triangle exists, or 2. So I'm going to describe what's happening here with these triangles for side, angle. And then when we do the examples, I'll show you how to determine whether no triangle exists, one triangle exists, or 2 triangle exists. All right, so starting with no triangles. So I'm going to label this side here side 1, this consecutive side 2, and that angle 1. So notice side length 1 is not long enough to complete the triangle. So since side 1 is not long enough to complete the triangle, no triangle exists. And when we do some examples, I will be showing you how to determine when no triangles exist. Okay, so second example. Here's side 1. Here's another consecutive side. And there's angle 1. And in this case, side 1 is long enough to create one triangle. So that means one triangle exists. And when we work on examples, I will show you how to determine when only one triangle exists. And now for two triangles. We'll label this angle angle 1. This will be side length 2. And this would be side length 1. And I'm going to label that side length 1 also. So side length 1 and angle 1 are small enough to create two triangles. So in the triangle on the left, I'm going to highlight the first triangle. This triangle has angle 1, side length 2, and side length 1. Over here to the right, there's angle 1, here's side length 2, just like our triangle on the left, and here is side length 1. So this would be the second triangle that is possible. So in this case, two triangles exist. And when we do the examples, I'll show you how to determine when two triangles exist. And now, I will prove that the law of sines is true. Okay, so first I'm going to make that c a lowercase c. And what's given, triangle ABC with sides lowercase a, lowercase b, and lowercase c. And you have a dashed line going from angle B down to side B. And that makes a 90-degree angle with side B. So now what I can do is if I label this H, I can create a sine formula for angle A. So we know that sine of A is equal to the opposite side, which would be H, divided by C, which would be the hypotenuse. I can do the same thing with angle C. Sine of angle C is equal to the opposite side, which would be H, divided by A. Now what I'm going to do is I'm going to solve for H in each of these equations. So H is equal to C sine of A, and H is equal to A sine of C. Now notice that both of these expressions that I'm about to highlight equal H. So I'm going to set those expressions equal to each other. So C sine of A is equal to A sine of C. Next, I'm going to divide both sides by C. So sine of A is equal to A sine of C divided by C. Next, I'm going to multiply both sides by 1 divided by A. So now sine of A divided by A is equal to sine of C divided by C. Now notice we left off angle B. However, a similar argument can be made by labeling angle C or angle A with angle B. So therefore, sine of capital A divided by A is equal to sine of capital B divided by B, which is equal to sine of capital C divided by C. And the proof is done.